All right, looking at the A-B worksheets for Chapter 5. We're going to do A and B in this one video because it's pretty short, only 3 questions total. So for Section A, starting off with number 1, so given a rational function, and remember a rational function is simply any function where you have a variable in the denominator. So they're telling us that x can't be 5, which obviously we know that because that would give us a 0 denominator, which you can't do. So that's also where the vertical asymptote comes from. So I'm going to kind of skip to number 2 real quick. So vertical asymptote is where you just set the denominator equal to 0 and solve. It's an asymptote because that's a value that x cannot equal. So if x cannot equal 5, that means we have a boundary line or an asymptote where x does equal 5. We're just stating that's an area where the graph can't go. But for the x-intercept, so if we just set the entire thing equal to 0, we find the x-intercepts. So remember, x-intercepts are where y is 0, y-intercepts are where x is 0. So if I were to set that entire equation equal to 0, that's like subbing in a 0 for y. So we can get the x-intercept that way. For this, remember that for the denominator part of this, since the whole thing equals 0, if I multiply this over to the right, it's times 0, so it still just becomes the numerator equal to 0. So really, whenever you're dealing with a rational function like this, or any fraction function, just setting the numerator equal to 0 will find the x-intercept because the denominator will always become 0 when you multiply it over anyway. So anyway, if we solve that, add the 12, divide by 3, and we can see that it's at x equals 4 for that guy. So we'd be looking at the point 40 for the x-intercept. So part 2 we already did. Equation of the horizontal asymptote. Really the easiest way to do that in a rational function where the top exponent is equal to the bottom exponent. This is x to the first, this is x to the first. All you have to do is divide their coefficients. So coefficient on top is a 3. The coefficient on bottom is -1. So if I just divide those, then I can see that where y equals -3 would be my horizontal asymptote. Really important, as I've trying to been hit on throughout all these videos, is you really have to read the directions carefully and do exactly what they say, or it costs people points on a test. So when it says write an equation, you got to write an equation. Like I did here. So if you just said -3 as your answer, you'd lose some credit for that because you didn't write an equation. So make sure you're reading those directions carefully on all your tests. As x grows large, what is the value that we are approaching? So this is just the idea of a limit. So as x is headed towards positive infinity, aka growing really, really large, what's the result that we are heading towards as that happens? So there's 2 ways we could figure that out. One is really just logically. If you consider x becoming super large, like let's just say you plugged in 1 billion for that x and 1 billion for that x. As this x becomes extremely large, these constants become insignificant. Because if I have 3 billion minus 12, that minus 12 has very little effect on the overall number because this is so large and this is so small. Same thing is happening on bottom. If x becomes extremely large, this little constant becomes pretty insignificant. So as x gets larger and larger and larger and larger, all that really matters at that point is the x's. Because whatever else is going on, these tiny constants are just going to have a less and less of an effect on the overall result as x gets really, really large. So what you're really looking at is just this idea right here. And so as x becomes really large, if we kind of reduce those or cancel those out, I'm left with just 3 over -1. So -3 becomes the limit that we are approaching. The other way to see that is sort of graphically. It's really defines the whole purpose of an asymptote, is it represents a limit. If you can look at this part of the graph on the right, as x becomes larger and larger and larger, meaning as you head towards positive infinity, on the x-axis, what is your graph approaching? Remember, we have a horizontal asymptote right here at -3 that runs right through this graph right here. So this boundary line, this y equals -3 boundary line, is the value that this graph is approaching as it heads to the right or as it heads towards infinity, but it would never actually touch this number. It forever gets closer and closer to it, but would never actually land on -3. You just forever get closer to -3. So that becomes the limit or the boundary that we are approaching as x gets really, really large or as x approaches infinity. And so that's where we just get the idea that it's just -3 is the value or the limit that we are approaching as x gets really large. So moving on to number 2, so given a new rational function that we see right here, and again, of course, x can't equal q because that would create a zero denominator which is undefined, and we can't do that. So they always throw in this type of notation for things like that. If they didn't put that in there, it's really still implied. We know that that's true, even if you didn't see that, but that's still a common notation that you'll expect to see. So write down the equations of the asymptotes of the graph. So remember, as far as this idea goes, same thing as up here. If you set the denominator equal to 0, so in this case we're just going to get x equaling q. Right, that always gives us the vertical asymptote. And for the horizontal asymptote, when we saw it up here, we just did coefficient over coefficient because the exponents were equal. This was x to the first and this was x to the first. However, when the exponent on bottom is larger, it automatically gives you a horizontal asymptote where y equals 0. If you ever get a case where the exponent on top is larger, then there is no horizontal asymptote. So those are the 3 cases that you can run into. So last part on this, so vertical and horizontal asymptotes to the graph intersect at point P. So these 2 graphs will intersect at point P. Obviously the y is 0 for that. So you can see the 5 is sitting in place of the q. So we know q must equal the 5 that we see right there. So as long as you kind of just recognize what you're looking at for that one, that's a pretty simple one to solve. Moving on down here to section B. So just one more question here. Just doing number 1 for this assignment. So given another rational function, and again, typical notation we expect to see, x is an element of the real number system and cannot equal -4. So find the vertical asymptote of the graph. Again, set the denominator equal to 0, and we're going to get x equals -4. So that's given to us really in 2 cases. This idea for what x cannot equal is also the asymptote. So we also know that based on this statement, x cannot equal -4, gives us a boundary line. So we're given that boundary or the asymptote where x does equal -4. But again, we can always get that by setting the denominator equal to 0. So horizontal asymptote of the graph, as we talked about on top, since the exponents are equal, x to the first, x to the first, we just divide the coefficients. So 3 divided by 1 gives us the horizontal asymptote for this one. Third part, where do these guys intersect? Well, if you have a vertical running through x equals -4 and a horizontal running through y equals 3, then these guys would have to intersect at the point -4, 3. So that's point P for this. So sketch the graph showing the asymptotes of the dotted line. So here's something where we could easily throw into a calculator to help us sketch. These guys, that's a pretty simple graph without a calculator to show where this is happening. For stuff like this, if it's a case where you don't have a calculator available, if it's a no calculator portion of the IB test or whatever's going on, you can always get by just plugging in a couple numbers and testing a few points. We know in general, whenever you have a rational function like this, with the asymptotes that we've already identified, so we got the y equals 3 running right through there. We got the x equaling -4 running right through there. So remember, rational functions take on 2 curves. So typically we either see a set of curves across from each other like this, or they're going to be across from each other here and here. So you might see curves like this and this. But again, if you plugged in a few numbers by hand, you could figure out where those curves are going to fall and just connect a few dots. So that's always something we could do by hand. If not, we can do it on the calculator if that's available for this one as well. So real quick on the calculator, go to your y equals and plug in the function that we're doing. Don't forget to put parentheses around the denominator. It's always important. I always put it numerator and denominator just to be safe. But anyway, if we take a look at the graph, here's what we got. Whenever you sketch a graph, you got to label a few things. So you always want to show some of the y-axis scaling as well as the x-axis scaling. So if you ever need some assistance with that, right here you go to the table. So in the table you can scroll up and down on this forever and get every value for these graphs under the sun, and so you can always plot a few points and get some specific values that way as well to help you with some accuracy on your graph. Alright, moving on. So that was our part B. Part C, they're giving us an equation y equals 4x plus 3 that's tangent to the graph, which just means it hits this graph at a point. So find the coordinates of t, which is this point of tangency. So we have this, they're calling line L, and the point where it hits our graph, this one, they're calling point T. So just looking for that one. Again, we can do this by hand or by calculator. A point of tangency we can find just by setting this function equal to this function and solving for x. So that's an option. We can do that, and you can do that by hand. You'd probably end up just solving a quadratic equation, which we can get. So that's one option. If it's a case where we're going to be using a calculator on something like that, this is a way you can do it in the calculator as well. If you take the graph that we already have and just throw in the new graph of 4x plus 3, then we can take a look, see where that graph intersects. So right here we have point T, which is our point of tangency. If you want to know where those guys intersect, probably the easiest way to spot that is to look at your table of values. I'm looking for where do they have a point in common. So if I go under my table, and if you scroll down right here, you'll notice at -2, they both have the same y coordinate. So that is the point of tangency where x equals -2. And we can see the result is -5. So for that one, that's one way to get your coordinates for point T. Again, the other way you would be doing that by hand is you just take your 4x plus 3, set it equal to the original function, and we just solve for x. So you would start by taking this guy, multiplying it over to the other side, and then just continue solving for x to solve the quadratic. So you have a little FOIL to do. Get everything onto one side so that it equals 0, and solve your quadratic, and we should come out with x equaling -2 if we did that right. And then you can always take your -2, plug it back in right there to solve for the y value. So you could plug it in there or there, whatever's easiest, should get the same result. Alright, so part D, line M is parallel to line L, which means they just have the same slope. So looking at this, the slope of line L was 4, which means the slope of line M is also going to be 4, and is tangent at point S where x equals -6. So we now know the x coordinate, we know the slope, we just need to come up with the y coordinate for this guy. So we already have the x, so all we have to do is sub that back into the function in order to get the y coordinate. Remember, it is tangent to this graph. So you got to sub it in for this x in order to get his y value. It does not connect with line L, so you can't sub it in right here. All we know is that it's parallel to line L. It doesn't mean it intersects line L, so we can't sub it in here. You got to go back to the original function, plug in a -6 for both x's, and we can get our y coordinate that way. If it's something where we have a graph handy or a calculator handy, we can do it on here as well. Let me get rid of this graph for just a minute. So if you look at the original graph, if I just want to sub in a -6 for x, I can go under Calc, choose Value, put -6, and hit Enter, and right there it gives you the y coordinate, which is 11. So that works too. So the y-coordinate is 11. Again, make sure that you read directions carefully on a test. If it just says find the y-coordinate, you only list the y-coordinate. You would not write this as an ordered pair because that's not what the directions ask for. So if you wrote this as an ordered pair, negative 6, 11, you can be docked for that because that's not the way the question is worded. So really important that you read those things carefully. Find the y-coordinate, so we only state the y-coordinate. And again, you could have done that one by hand too. Just plug in the negative 6 right there for x. You should also come out with 11. So find an equation of the line. This is where we use our point slope formula. So the way it's given to us in our formula packet is slightly different than the way you might have learned it in the past, but the way it's in our formula packet, we do y minus y over x minus x equals our slope, which we know is 4 because the lines are parallel. And so this is what they call point slope form or gradient form. Since this is written in the form of a gradient or a slope, since we did y minus y over x minus x. But if we do a little cleanup, the common way of writing these is to put it into y equals mx plus b form. So I'm going to multiply my x plus 6 over to the right. And distribute that 4. Add the 11 over. All right, let me slide that up. So add the 11 over, and there you go. This is another case, though, especially with writing equations of lines. Always read directions on a test carefully. Oftentimes, they'll ask you to put it in a different form. Sometimes they want everything onto one side so that the whole thing equals 0. Sometimes, if you have fractions, they might throw in something like this, where they say something that all the letters, the x and y, must be elements of the integer system, which means you can't have fractions, so you got to multiply through by something to clear out all the fractions. Little things like that. So really important that you read carefully with the notation and on a test how they want you to write your answers. So that was that part. Last part is part E. Show that P is the midpoint of TS. So if we find our points for T and S. So we already know that point S was negative 6, 11. And point T, right up here, we had negative 2, negative 5. Oops. So midpoint, we just know that's where you basically find the average. So if we add our x's, divide it by 2, add the y's, divide those by 2, simplify that out, we should get point P if we do this correctly. So a little cleanup on those. So I'm looking at negative 8 over 2, which is negative 4. Looking at 6 over 2, which is 3. So there we go. We are showing that that is equal to point P.